Hello, Namaste. Myself Ankita Shreya Prasad, and you are listening to Along With, our NCERT 11th and 12th audio video book, presented by ART.SKILL.PASSION.
Chapter 7, Alternating Current. 7.1 Introduction. We have so far considered direct current DC sources and circuit with DC sources. These circuits do not change direction with time, but voltages and currents that vary with time are very common. The electric main supply in our houses and offices is a voltage that varies like a sine function with time. Such a voltage is called alternating voltage, AC voltage, and the current driven by it in a circuit is called the alternating current, AC current. Today, most of the electrical devices we use require AC voltage. This is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage over DC voltage is that AC voltage can be easily and efficiently converted from one voltage to the other by means of transformers. Further, electrical energy can also be transmitted economically over long distances. AC circuits exhibit characteristics which are exploited in many devices of daily use. For example, whenever we tune our radio to a favorite station, we are taking advantage of a special property of AC circuits, one of many that you will study in this chapter. 7.2 AC voltage applied to a resistor. Figure 7.1 show a resistor connected to a source epsilon of AC voltage. The symbol of an AC source in a circuit diagram is, we consider a source which produces sinusoidally varying potential difference across its terminals. Let this potential difference, also called AC voltage, be given by V is equal to Vm sin omega t, where Vm is the amplitude of the oscillating potential difference and omega is its angular frequency. Figure 7.1 AC voltage applied to a resistor. To find the value of current through the resistor, apply Kirchhoff's loop rule. Sigma epsilon t is equal to 0. Refer to section 3.13 to current shown in figure 7.1 to get Vm sin omega t is equal to IR. I is equal to Vm divided by R sin omega t. Since R is a constant, we can write this equation as I is equal to Im sin omega t, where the current amplitude Im is given by Im is equal to Vm by R. Equation 7.3 is Ohm's law, which for resistors works equally well for both AC and DC voltage. The voltage across a pure resistor and the current through it, given by equation 7.1 and 7.2, are plotted as a function of time in figure 7.2. Note in particular that both V and I reach 0 minimum and maximum values at the same time. Clearly, the voltage and current are in phase with each other. We see that like the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of instantaneous current values over one complete cycle is 0 and the average current is 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electrical energy. As you know, joule heating is given by I square R and depends on I square, which is always positive whether I is positive or negative and not on I. Thus, there is joule heating and dissipation of electrical energy when an AC current passes through a resistor. The instantaneous power dissipated in the resistors is P is equal to I square R is equal to I square M R sine square omega t. The average value of P over a cycle is
P dash is equal to lesser than I square R greater than is equal to lesser than I square M R sine square omega t greater than. With the bar over a letter, here P denotes as average value and lesser than and greater than denotes taking average of quantity inside the bracket, since I square M and R are constants. P dash I square M R lesser than sine square omega t greater than. Using the trigonometric identity, sine square omega t is equal to 1 by 2 1 minus cos 2 omega t. We have sine square omega t is equal to 1 by 2 1 minus lesser than cos 2 omega t greater than, and since lesser than cos 2 omega t greater than is equal to 0, we have lesser than sine square omega t greater than is equal to 1 by 2. Thus, P dash is equal to 1 by 2 I square M R. To express AC power in the same form as DC power, P is equal to I square R. A special value of current is defined and used. It is called root mean square RMS or effective current, figure 7.3, and is denoted by I RMS or I. The average value of function ft over a period t is given by lesser than ft greater than is equal to 1 by t integral t0 ft into d theta. Lesser than cos omega t greater than is equal to 1 by t integral t0 cos 2 omega t d theta is equal to 1 by t sin 2 omega t by 2 omega is equal to 1 by 2 omega t sin 2 omega t minus 0 is equal to 0. It is defined by I is equal to root over I square dash is equal to root over 1 by 2 I square M is equal to I M divided by root 2 is equal to 0.707 I M. In terms of I, the average power denoted by P is equal to P dash is equal to 1 by 2 I square M R is equal to I square R. Similarly, we define the RMS voltage or effective voltage by V is equal to Vm divided by root 2 is equal to 0.707 Vm. From equation 7.3, we have Vm is equal to IMR or Vm divided by root 2 is equal to Im divided by root 2R or V is equal to IR. Equation 7.9 gives the relation between AC current and AC voltage and is similar to that in the DC case. This shows the advantage of introducing the concept of RMS values. In terms of RMS values, the equation of power, equation 7.7, and relation between current and voltage in AC circuits are essentially the same as those for the DC case. It is customary to measure and specify RMS values for AC quantities. For example, the household line voltage of 220 volt
is an RMS value with a peak voltage of Vm is equal to root 2 V is equal to 1.414 into 220 volt is equal to 311 volt. In fact, the I or RMS current is the equivalent DC current that would produce the same average power loss as the alternating current. Equation 7.7 can also be written as P is equal to V square divided by R is equal to IV, since V is equal to IR. 7.3 Representation of AC current and voltage by rotating vectors phase source. In the previous session, we learned that the current through a resistor in a phase with the AC voltage, but this is not so in the case of an inductor, a capacitor, or a combination of these circuit elements. In order to show phase relationship between voltage and current in an AC circuit, we use the notation of phasors. The analyzing of an AC circuit is facilitated by the use of phasors diagram. A phasor is a vector which rotates about the origin with angular speed omega. As shown in figure 7.4, the vertical components of phasors V and I represent the sinusoidally varying quantities V and I. The magnitude of phasors V and I represent the amplitudes of the peak values Vm and Im of these oscillating quantities. Figure 7.4a show the voltage and current phasors and their relationship at time t1 for the case of an AC source connected to a resistor that is corresponding to the circuit shown in figure 7.1. The projection of voltage and current phasors on vertical axis, that is Vm sin omega t and Im sin omega t, respectively, represent the value of voltage and current at the instant as they rotate with frequency omega. Curves in figure 7.4b are generated. From figure 7.4a, we see that phasors V and I for the case of a resistor are in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is 0. 7.4 AC voltage applied to an inductor. Figure 7.5 show an AC source connected to an inductor. Usually inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance, thus the circuit is purely inductive AC circuit. Let the voltage across the source be V is equal to Vm sin omega t using the Kirchhoff loop rule. Sigma epsilon t is equal to 0, and since there is no resistor in the circuit, V minus L di by dt is equal to 0. Where the second term is the self-induced Faraday EMF in the inductor and L is the self-inductance of the inductor. The negative sign follows from Lenz's law. Combining equation 7.1 and 7.10, we have di by dt is equal to V by L is equal to Vm by L sin omega t. Equation 7.11 implies that the equation for it, the current as a function of time, must be such that a slope di by dt is a sinusoidally varying quantity with the same phase as the source voltage and an amplitude given by Vm by L. To obtain the current, we integrate di by dt with respect to time. Integral di by dt into dt Vm by L integral sin omega t dt and get I is equal to minus Vm by omega L cos omega t plus constant. The integration constant has the dimension of current and is time independent. Since the source has an EMF which oscillates symmetrically about 0. The current it sustains also oscillates symmetrical about 0, so that no constant or time independent component of the current exists. Therefore, the integration constant is 0 using minus cos omega t is equal to sine into omega t minus pi by 2. We have I is equal to Im sine into omega t minus pi by 2, where Im is equal to Vm divided by omega L is the amplitude of the current. The quantity omega L is analogous to the resistance and is called inductive reactance denoted by XL. XL is equal to omega L. The amplitude of current is then Im is equal to Vm divided by XL. The dimension of inductive reactance is the same as that of resistance and its SI unit is ohm. The inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of current. A comparison of equation 7.1 and 7.12 for the source voltage and the current in an inductor show that the current lags the voltage by pi by 2 or 1/4 1/4 cycle. Figure 7.6a shows the voltage and the current phases. In the present case, at instant t1, the current phasors I is pi by 2 behind the voltage phasors V. When rotated with frequency omega counterclockwise, they generate the voltage and current given by equation 7.1 and 7.12 respectively, and as shown in figure 7.6b. Figure 7.6a, a phasor diagram for the circuit. In figure 7.5b, graph of V and I versus omega t. We see that the current reaches its maximum value later than the voltage by 1/4 of a period. T divided by 4 is equal to omega 2 by omega. You have seen that inductor has reactance that limits current similar to resistance in a DC circuit. Does it also consume power like a resistance? Let us try to find out. The instantaneous power supplied to the inductor is PL is equal to IV is equal to Im sine into omega t minus pi by 2 into Vm sine omega t is equal to minus Im Vm cos omega t sine omega t is equal to minus Im Vm divided by 2 sine 2 omega t. So the average power over a complete cycle is PL is equal to minus Im Vm divided by 2 sine into 2 omega t is equal to minus Im Vm divided by 2 sine 2 omega t is equal to 0, since the average of sine 2 omega t over a complete cycle is 0. Thus the average power supplied to an inductor over one complete cycle is 0. Figure 7.7 explains it in detail. 0 to 1. Current I through the coil entering at A increases from 0 to a maximum value. Flux lines are sent up, that is, the core gets magnetized. With the polarity shown, voltage and current are both positive. So their product P is positive. Energy is absorbed from the source. 1 to 2. Current in the coil is still positive but is decreasing. The core gets demagnetized and the net flux becomes 0 at the end of a half cycle. The voltage V is negative since di by dt is negative. The product of voltage and current is negative and energy is being returned to source. One complete cycle of voltage current. Note that the current lags the voltage. 2 to 3. current I becomes negative, that is, it enters at B and comes out of A. Since the direction of current has changed, the polarity of the magnet changes. The current and voltage are both negative, so the product P is positive, energy is absorbed. 3 to 4. Current I decreases and reaches its zero value at 4 when core is demagnetized and flux is 0. The voltage is positive but the current is negative. The power is therefore negative. Energy absorbed during the cycle 2 to 3 is returned to the source. Figure 7.7. Magnetization and demagnetization of an inductor. 7.5. AC voltage applied to a capacitor. Figure 7.8 shows an AC source Epson generating AC voltage V is equal to Vm sin omega t connected to a capacitor only. A purely capacitive AC circuit when a capacitor is connected to a voltage source. In a DC circuit, current will flow for the short time required to charge the capacitor. As charge accumulates on the capacitor plates, the voltage across them increases, opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it charges. When the capacitor is fully charged, the current in the circuit falls to 0. When the capacitor is connected to an AC source, as in figure 7.8, it limits or regulates the current, but does not completely prevent the flow of charge. The capacitor is alternatively charged and discharged. As the current reverses each off cycle, let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor is V is equal to Q by C. From Kirchhoff loop rule, the voltage across the source and the capacitor are equal. Vm sin omega t is equal to Q by C. To find the current, we use the relation I is equal to dQ by dt. I is equal to d by dt. Vmc sin omega t is equal to omega c Vm cos omega t. Using the relation cos omega t is equal to sin omega t plus pi by 2, we have I is equal to Im sin into omega t plus pi by 2, where the amplitude of the oscillating current is Im is equal to omega c Vm. We can rewrite it as Im is equal to Vm divided by 1 divided by omega c. Comparing it to Im is equal to Vm divided by R for a purely resistive current circuit, we find that 1 by omega c plays the role of resistance. It is called capacitive reactance and is denoted by Xc. Xc is equal to 1 by omega c, so that the amplitude of the current is Im is equal to Vm divided by Xc. The dimension of capacitive reactance is the same as that of resistance and its SI unit is ohm. The capacitive reactance limits the amplitude of the current in purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit, but it is inversely proportional to the frequency and the capacitance. A comparison of equation 7.16 with the equation of source voltage. Equation 7.1 shows that the current is pi by 2 ahead of voltage. Figure 7.9. A shows the phasor diagram at instant t. Here the current phasor 1 is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. Figure 7.9b shows the variation of voltage and current with time. We see that the current reaches the maximum value earlier than the voltage by 1/4 of a period. The instantaneous power supplied to the capacitor is PC is equal to IV is equal to Im cos omega t into Vm sin omega t is equal to Im Vm cos omega t into sin omega t is equal to Im Vm divided by 2 sin 2 omega t. So as in the case of an inductor, the average power PC is equal to Im Vm divided by 2 sin 2 omega t is equal to Im Vm divided by 2 sin 2 omega t is equal to 0. Since lesser than sin 2 omega t greater than is equal to 0 over a complete cycle, figure 7.10 explains it in detail. Thus we see that in the case of an inductor, the current lags the voltage by pi by 2, and in the case of a capacitor, the current leads the voltage by pi by 2. 0 to 1, the current I flows as shown, and from the maximum at 0 reaches a 0 value at 1. The plate A is charged to the positive polarity while negative charge Q builds up in B, reaching a maximum at 1 until the current becomes 0. The voltage Vc is equal to Q by C is in phase with Q and reaches maximum value at 1. Current and voltage are both positive, so P is equal to Vc, I is positive, energy is absorbed from the source during this quarter cycle as the capacitor is charged. 1 to 2, the current I receives its direction. The accumulated charge is depleted, that is, the capacitor is discharged during this quarter cycle. The voltage gets reduced but is still positive. The current is negative, their product, the power is negative. The energy absorbed during the 1/4 cycle 0 to 1 is returned during this quarter. One complete cycle of voltage by current. Note that the current leads the voltage. 2 to 3, as I continues to flow from A to B, the capacitor is charged to reverse polarity, that is, the plate B acquires positive and A acquires negative charge. Both the current and the voltage are negative, their product P is positive. The capacitor AB absorbs energy during this 1/4 cycle. 3 to 4, the current I reverses its direction at 3 and flows from B to A. The accumulated charge is depleted and the magnitude of the voltage Vc is reduced. Vc becomes 0 at 4 when the capacitor is fully discharged. The power is negative. Energy absorbed during 2 to 3 is returned to the source. Net energy absorbed is 0. Figure 7.10 Charging and discharging of a capacitor. 7.6 AC voltage applied to a series LCR circuit. Figure 7.12 shows a series LCR circuit connected to an AC source epsilon. As usual, we take the voltage of the source to be V is equal to Vm sin omega t. If Q is the charge on the capacitor and I the current at time t, we have from Kirchhoff loop rule L di by dt plus IR plus Q by C is equal to V. We want to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. We shall solve this problem by two methods. First, we use the technique of Fassos, and in the second method, we solve equation 7.20 analytically to obtain the time dependence of I. 7.6.1 Fassos diagram solution. From the circuit shown in figure 7.12, we see that the resistor, inductor and capacitor are in series. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase. Let it be I is equal to Im since sin omega t plus integral naught, where naught is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learned in the previous sessions, we shall construct a phasor diagram for the present case. Let first be the phasor representing the current in the circuit as given by equation 7.21. Further, let VL, VR, VC and V represent the voltage across the inductor, resistor, capacitor and the source respectively. From previous session, we know that VR is parallel to I, VC is pi by 2 behind I and VL is pi by 2 ahead of I. VL, VR, VC and I are shown in figure 7.13a with appropriate phase relations. The length of these phasors or the amplitude of VR, VC and VL are V is equal to Rm, Vrm is equal to IMR, VCM is equal to Im, XC, VLM is equal to Im, XL. The voltage equation 7.20 for the circuit can be written as VL plus VR plus VC is equal to V. The phasor relation whose vertical component gives the above equation is VL plus VR plus VC is equal to V. This relation is represented in figure 7.13b. Since VC and VL are always along the same line and in opposite direction, they can be combined into a single phasor VC plus VL, which has a magnitude VC minus VL since V is represented as the hypotenuse of a right triangle whose sides are VR and VC plus VL. The Pythagorean theorem gives Vm squared is equal to Vrm squared plus Vcm minus Vlm squared. Substituting the values of Rm, Vc and Vlm from equation 7.22 into the above equation, we have Vm squared is equal to Im squared plus Im xc minus Im xl whole squared is equal to I square m into r squared plus xc minus xl whole squared, or Im is equal to Vm divided by root over r squared plus xc minus xl whole squared. By analogy to the resistance in a circuit, we introduce the independence that in an AC circuit, Im is equal to Vm by Z, where Z is equal to root over x squared plus xc minus xl whole squared. Since phasor I is always parallel to the phasor VR, the phase angle naught is the angle between VR and V and can be determined from figure 7.4. Tan theta is equal to Vcm minus Vlm divided by Vrm. Using equation 7.22, we have tan theta is equal to xc minus xl divided by r. Equation 7.26 and 7.27 are graphically shown in figure 7.14. This is called impedance diagram, which is a right triangle with Z as its hypotenuse. Equation 7.25a gives the amplitude of the current and equation gives the phase angle. With these, equation 7.21 is completely specified. If xc greater than xl naught is positive and the circuit is predominantly capacitive, Consequently, the current in the circuit leaves the source voltage f Xc lesser than XL. Integral naught is negative and the circuit is predominantly inductive. Consequently, the current in the circuit lacks the source voltage. Figure 7.15 shows the phasor diagram and variation of V and I with omega t for the cases Xc greater than XL. Thus, we have obtained the amplitude and phase of circuit for an LCR series circuit. Using the technique of phasors, but this method of analyzing AC circuits suffers from certain disadvantages. First, the phasor diagram say nothing about the initial condition. One can take any arbitrary value of t, say t1, as done throughout this chapter, and draw different phasors which show the relative angle between different phasors. The solution so obtained is called the steady state solution. This is not a general solution. Additionally, we do have a transient solution which exists even for V is equal to 0. The general solution is the sum of the transient solution and the steady state solution. After a sufficiently long time, the effects of the transient solution die out and the behavior of the circuit is described by the steady state solution. 7.6.2 Analytical solution. The voltage equation for the circuit is L di by dt plus Ri plus Q by C is equal to V is equal to Vm sin omega t. We know that I is equal to dq by dt, therefore di by dt is equal to d square q divided by dt square. Thus, in terms of q, the voltage equation becomes L d square q divided by dt square plus R dq by dt plus q by C is equal to Vm sin omega t. This is like the equation for a forced damped oscillator. In class 11 physical textbook, let us assume a solution Q is equal to Qm sin omega t plus theta, so that dq divided by dt is equal to Qm omega cos omega t plus theta, and d square q by dt square is equal to minus Qm omega square sin omega t plus theta. Substituting these values in equation, we get Qm omega r cos omega t plus theta plus xc minus xl sin omega t plus theta is equal to Vm sin omega t, where we have used the relation xc is equal to 1 by omega c, xl is equal to omega l. Multiplying and dividing equation 7.30 by z is equal to root over r square plus xc minus xl whole square. We have Qm omega z into r by z cos omega t plus theta plus xc minus xl divided by z sin omega t plus theta is equal to Vm sin omega t. Now let r by z is cos theta and xc minus xl by z is equal to sin theta, so that theta is equal to tan inverse xc minus xl divided by r. Substituting this equation 7.31 and simplifying, we get Qm omega z cos into omega t plus theta minus integral is equal to Vm sin omega t. Comparing the two sides of this equation, we see that Vm is equal to Qm omega z is equal to Im z, where Im is equal to Qm omega, and theta is equal to integral naught is equal to minus q pi by 2, or theta is equal to minus pi by 2 plus integral naught. Therefore, the current in the circuit is I is equal to dq by dt is equal to qm omega cos omega t plus theta is equal to Im cos into omega t plus theta, or I is equal to Im sin omega t plus loop integral, where Im is equal to Vm divided by Z is equal to Vm divided by root over r squared plus xc minus xl whole squared, and integral is equal to tan inverse xc minus xl divided by r. Thus, the analytical solution for the amplitude and phase of the current in the circuit agrees with that obtained by the technique of phases. 7.6.3 Resonance. An interesting characteristics of the series RCL circuit is the phenomenon of resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. A familiar example of this phenomenon is a child on a swing. The swing has a natural frequency for swinging back and forth like a pendulum. If the child pulls on the rope at regular intervals and the frequency of the pulse is almost the same as the frequency of swinging, the amplitude of the swinging will be large. Chapter 14, Class 11th. For an RCL circuit driven with voltage of amplitude Vm and frequency omega, we found that the current amplitude is given by Im is equal to Vm divided by Z is equal to Vm divided by root r square plus xc minus xl whole square, with xc is equal to 1 divided by omega c and xl is equal to omega l. So, if omega is varied, then at particular frequency omega naught xc is equal to xl and the impedance is minimum. Z is equal to root over x square plus 0 square is equal to r. This frequency is called the resonance frequency. Xc is equal to xl, or 1 divided by omega naught c is equal to omega naught l, or omega naught is equal to 1 divided by root over lc. At resonant frequency, the current amplitude is maximum. Im is equal to Vm divided by r. Figure 7.16 shows the variation of Im with omega in a RLC series circuit with L is equal to 1.00 mH, C is equal to 1.00 Nf for two values of R. I is equal to R is equal to 100 omega, and second R is equal to 200 omega for the source. Applied Vm is equal to 100 volt. Omega naught for this case is 1 divided by root LC is equal to 1.00 into 10 to the power 6 rads per second. We see that the current amplitude is maximum at the resonant frequency, since Im is equal to Vm divided by R at resonance. The current amplitude for case 1 is twice to that for case 2. Resonance circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set, the antenna of a radio accepts signals from many broadcasting ratios. The signal picked up in the antenna acts as a source in the tuning circuit of radio, so the circuit can be driven at many frequencies. But to hear one particular radio stations, we tune the radio. In tuning, we vary the capacitance of capacitor in tuning circuit such that resonant frequency of circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with the frequency of the signal of particular radio station in the circuit is maximum. It is important to note that resonance phenomenon is exhibited by a circuit only if both L and C are present in the circuit. Only then do the voltages across L and C cancel each other, both being out of phase, and the current amplitude is Vm divided by R, the total source voltage appearing across R. This means that we cannot have resonance in a RL or RC circuit. Sharpness of resonance. The amplitude of the current in the series LCR circuit is given by Im is equal to Vm divided by root over R square plus omega L minus 1 divided by omega C whole square, and is maximum when omega is equal to omega naught is equal to 1 by divided by root over LC. The maximum value is I max M Vm divided by R. For values of omega other than omega naught, the amplitude of the current is less than the maximum value. Suppose we choose a value of omega for which the current amplitude is 1 divided by root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. From the curve in figure 7.16, we see that there are two such values of omega, say omega 1 and omega 2, one greater and the other smaller than omega naught and symmetrical about omega naught. We may write omega 1 is equal to omega naught plus delta omega, omega 2 is equal to omega naught minus delta omega. The difference omega 1 minus omega 2 is equal to 2 delta omega is often called the bandwidth of the circuit. The quantity omega naught divided by 2 delta omega is regarded as a measure of the sharpness of resonance. The smaller the delta omega, the sharper or the narrow is the resonance. To get an expression for delta omega, we note that the current amplitude Im is 1 divided by root 2 I max M for omega 1 is equal to omega naught plus delta omega. Therefore, at omega 1, Im is equal to Vm divided by root over R square plus omega 1 L minus 1 divided by omega 1 C whole square is equal to I max M divided by root 2 is equal to Vm divided by R root 2, or root over R square plus omega 1 L minus 1 omega 1 C whole square is equal to R root 2, or R square plus omega 1 L minus 1 divided by omega 1 C whole square is equal to 2 R square is equal to omega 1 L minus 1 divided by omega 1 C is equal to R, which may be written as omega naught plus delta omega L minus 1 divided by omega naught plus delta omega C is equal to R. Omega L into 1 plus delta omega by omega naught minus 1 divided by omega naught C into 1 plus delta omega divided by omega naught is equal to 0. Using omega naught square is equal to 1 by LC in the second term on the left hand side, we get omega naught L 1 plus delta omega divided by omega naught minus omega naught L divided by 1 plus delta omega divided by omega naught is equal to R. We can approximate 1 plus delta omega divided by omega naught whole to the power minus 1 as 1 minus delta omega divided by omega naught since delta omega divided by omega naught lesser than 1. Therefore, omega naught L into 1 plus delta omega by omega naught minus omega naught L into 1 minus delta omega divided by omega naught is equal to R, or omega naught L to delta omega divided by omega naught is equal to R. Delta omega is equal to R divided by 2L. The sharpness of resonance is given by omega naught divided by 2 delta omega is equal to omega naught L divided by R. The ratio omega naught L divided by R is also called the quality factor Q of the circuit. Q is equal to omega naught L divided by R. From equation 7.36b and 7.36c, we see that 2 delta omega is equal to omega naught divided by Q. So, larger the value of Q, the smaller is the value of 2 delta omega, or the bandwidth, and sharper is the resonance. Using omega square naught is equal to 1 divided by LC, equation 7.36c, and can be equivalently expressed as Q is equal to 1 divided by omega naught CR. We see from figure 7.15 that if the resonance is less sharp, not only the maximum current is less, the circuit is close to resonance for a large range delta omega of frequencies, and the tuning of the circuit will not be good. So, less sharp the resonance, less is the selectivity of the circuit, or vice versa. From equation 7.36, we see that if quality factor is large, that is R is low or L is large, the circuit is more selective. 7.7 Power in AC circuit. The power factor, we have seen that a voltage V is equal to Vm sin omega t applied to a series RLC circuit drives a circuit in the circuit given by I is equal to Im sin omega t plus integral naught, where Im is equal to Vm divided by Z and integral naught is equal to tan inverse into Xc minus XL divided by R. Therefore, the instantaneous power P supplied by the source is P is equal to Vi is equal to Vm sin omega t into Im sin omega t plus integral naught is equal to Vm Im divided by 2 cos integral naught cos 2 omega t plus integral naught. The average power over a cycle is given by the average of the two terms in RHS of equation 7.37. It is only the second term which is the time dependent, as average is 0. The positive half of the cosine cancels the negative half. Therefore, P is equal to Vm Im divided by 2 cos integral naught is equal to Vm divided by root 2 Im divided by root 2 cos integral naught is equal to Vi cos integral naught. That this can also be written as P is equal to I square Z cos integral naught. So, the average power dissipated depends not only on the voltage and current but also on the cosine of the phase angle of integral naught between them. The quantity cos integral naught is called the power factor. Let us discuss the following cases. Case 1. Resistive circuit. If the circuit contains only pure R, it is called resistive. In that case, integral naught is equal to 0, cos integral naught is equal to 1. There is maximum power dissipation. Case 2. Purely inductive or capacitive circuit. If the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos integral naught is equal to 0 and no power is dissipated. Even though a current is flowing in the circuit, the current is sometimes referred to as voltless current. Case 3. LCR series circuit. In an LCR series circuit, power dissipated is given by equation 7.38, where integral naught is equal to tan inverse Xc minus XL divided by R. So integral naught may be 0 in RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. Case 4. Power dissipated at resonance in LCR circuit. At resonance, Xc minus XL is equal to 0 and integral naught is equal to 0. Therefore, cos integral naught is equal to 1 and P is equal to I square Z is equal to I square R. That is, maximum power is dissipated in a circuit through R at resonance. 7.8. LC oscillation. We know that a capacitor and an inductor can store electrical and magnetic energy respectively. When a capacitor initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomena of electrical oscillation similar to oscillation in mechanical systems. Chapter 14, Class 11th. Let a capacitor be charged Qm at t is equal to 0 and connected to an inductor as shown in figure 7.18. The moment that current is completed, the charge on the capacitor starts decreasing, giving rise to the current in the circuit. Let Q and I be the charge and current in the circuit at time t. Since di divided by dt is positive, the induced EMF in L will have polarity as shown, that is VB lesser than VA according to Kirchhoff loop rule. Q divided by C minus L di by dt is equal to 0. I is equal to minus dq divided by dt in the present case. As Q decreases, I increases. Therefore, equation 7.39 becomes d squared Q divided by dt squared plus 1 divided by LC into Q is equal to 0. The equation as the form d square x divided by dt square plus omega squared 2x is equal to 0 for a simple harmonic oscillator. The charge on the capacitor therefore oscillates with a natural frequency omega naught is equal to 1 by root LC and varies sinusoidally with times as Q is equal to Qm cos omega naught t plus integral naught, where Qm is the maximum value of Q and integral naught is a phase constant. Since Q is equal to Qm at t is equal to 0, we have cos integral naught is equal to 1 or integral naught is equal to 0. Therefore, in the present case, Q is equal to Qm cos omega naught t. The current I is equal to minus dq divided by dt is given by I is equal to Im sin omega naught t, where Im is equal to omega naught Qm. Let us now try to visualize how this oscillation takes place in the circuit. Figure 7.19 shows a capacitor with initial charge Qm connected to an ideal inductor. The electrical energy stored in the charged capacitor is UE is equal to 1 by 2 Q square M divided by C. Since there is no current in the circuit, energy in the inductor is 0. Thus, the total energy of LC circuit is U is equal to UE is equal to 1 by 2 Q square M by C. Figure 7.19. The oscillation in an LC circuit are analogous to the oscillation of the block at the end of a spring. The figure depicts one half of a cycle. At t is equal to 0, the switch is closed and the capacitor starts to discharge. Figure 7.19b, as the current increases, it sets up a magnetic field in the inductor, and thereby some energy gets stored in the inductor in form of magnetic energy. UB is equal to 1 by 2 Li square as the current reaches its maximum value Im at T is equal to T divided by 4 as in figure 7.19c. All the energy is stored in the magnetic field. UB is equal to 1 by 2 Li square M. You can easily check that the maximum electrical energy equals the maximum magnetic energy. The capacitor now has no charge and hence no energy. The current now starts charging the capacitor as in figure 7.19d. This process continues till the capacitor is fully charged at T is equal to T divided by 2, figure 7.19e, but is charged with a polarity opposite to its initial state in figure 7.19a. The whole process is described with no repeat itself till the system reverts to its original state. Thus, the energy in the system oscillates between the capacitor and the inductor. The LC oscillates is similar to the mechanical oscillation of a block attached to a spring. The lower part of each figure in figure 7.19 depicts the corresponding stage of a mechanical system. A block attached to a spring, as noted earlier, for a block of a mass m oscillating with frequency omega naught. The equation is d square x divided by dt square plus omega square naught x is equal to 0. Here omega naught is equal to root over k divided by m, and k is the spring constant, so x corresponds to q. In case of a mechanical system, F is equal to ma is equal to m into dv divided by dt is equal to m into d square x divided by dt square. For an electrical system, epsilon is equal to minus L into di divided by dt is equal to minus L d square q divided by dt square. Comparing these two equations, we see that L is analogous to mass m. L is a measure of resistance to change in current. In case of LC circuit, omega naught is equal to 1 divided by root LC, and for mass on spring, omega naught is equal to root over k by m. So 1c is analogous to k. The constant k is equal to F divided by x tells us the external force required to produce a unit displacement, where 1 divided by c is equal to v by q tells us the potential difference required to store a unit charge. Table 7.1 gives the analogy between the mechanical and electrical quantities. Table 7.1 Analogies between mechanical and electrical quantities. Note that the above discussion of LC oscillations is not realistic for two reasons. First, every inductor has some resistance. The effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and the oscillations finally die away. Second, even if the resistance were zero, the total energy of the system would not remain constant. It is radiated away from the system in the form of electromagnetic waves, discussed in the next chapter. In fact, radio and TV transmitters depends on this radiation. 7.9 Transformers. For many purposes, it is necessary to change or transform an alternating voltage from one to another of greater or smaller value. This is done with a device called transformer using the principle of mutual induction. A transformer consists of two sets of coils insulated from each other. They are wound on a soft iron core, either one on top of the other, as in figure 7.20A on separate limbs of the core as in figure 7.20B. One of the coils called the primary coil has NP turns. The other coil is called the secondary coil. It has NS turns. Often the primary coil is the input coil and the secondary coil is the output coil of the transformer. When an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF in it. The value of this EMF depends on the number of turns in the secondary. We consider an ideal transformation in which the primary has negligible resistance and all the flux in the core links both primary and secondary windings. Let integral naught be the flux in each turns in the core at time t due to current in the primary when a voltage Vp is applied to it. Then the induced EMF or voltage epsilon s in the secondary with ns turns. Epsilon s is equal to minus ns d integral naught divided by dt, the alternating flux. Integral naught also includes an EMF called back EMF in primary. This is epsilon p is equal to minus np d integral naught divided by dt. But epsilon p is equal to Vp. If this were not so, the primary current would be infinite since the primary has zero resistance as assumed. If the secondary is an open circuit or the current taken from it is small, then to a good approximation, epsilon s is equal to Vs, where Vs is the voltage across the secondary. Therefore, equation 7.45 and 7.46 can be written as Vs is equal to minus Ns d integral naught divided by dt. Vp is equal to minus Np d integral naught divided by dt. From equation 7.45a and 7.46a, we have Vs by Vp is equal to Ns by Np. Note that the above relation has been obtained using three assumptions. First, the primary resistance and current are small. Second, the same flux inside both the primary and secondary as very little flux escape from the core. And third, the secondary current is small. If the transformer is assumed to be 100% efficient, no energy loses. The power input is equal to the power output, and since P is equal to IV, IP, Vp is equal to Is, Vs, although some energy is always lost. This is a good approximation since a well-designed transformer may have an efficiency of more than 95%. Combining equation 7.47 and 7.48, we have Ip by Is is equal to Vs by Vp is equal to Ns by Np. Since I and V both oscillate with the same frequency as the AC source, equation 7.49 also gives the ratio of the amplitudes or RMS values of corresponding quantities. Now we can see how a transformer affects the voltage and current. We have Vs is equal to Ns by Np into Vp and Is is equal to Np by Ns into Ip. That is, if the secondary coil has a greater number of turns than the primary, Ns greater than Np, the voltage is stepped up. Vs greater than Vp. This type of arrangement is called a setup transformer. However, in this arrangement there is less current in the secondary than in the primary. Np by Ns lesser than 1 and Is lesser than Ip. For example, if the primary coil of transformer has 100 turns and the secondary has 200 turns, Ns divided by Np is equal to 2 and Np divided by Ns is equal to 1 by 2. Thus 220 volt input at 10 ampere will set up to 440 volt output at 5.0 ampere. If the secondary coil has less turns than the primary, Ns lesser than Np, we have a step down transformer. In this case, Vs lesser than Vp and Is greater than Ip, that is, the voltage is stepped down or reduced and the current is increased. The equation obtained above apply the ideal transformers without any energy losses. But in actual transformers, small energy losses do occur due to the following reasons. First, flux leakage. There is always some flux leakage, that is, not all of the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. It can be reduced by the design of the core or the air gaps in the core. It can be reduced by the winding the primary and secondary coils one over the other. Second, resistance of windings. The wire used for the winding has some resistance and so energy is lost due to heat produced in the wire. I2R in high current, low voltage windings. These are minimized by using thick wire. Third, eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by using a laminated core. Fourth, hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to minimum by using a magnetic material which has a low hysteresis loss. The large-scale transmission and distribution of electrical energy over long distances is done with the use of transformers. The voltage output of the generator is stepped up so that the current is reduced and consequently the I2R losses is cut down. It is transmitted over long distances to an area substation near the consumers. There the voltage is stepped down. It is further stepped down disturbing the substations and utility poles before a power supply of 240 volt reaches our homes.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.